Hello there. Welcome to CERN, the European Laboratory for Particle Physics. We're here at the ATLAS experiment on the Large Hadron Collider at CERN. My name is Stephen Goldfarb and I am a physicist on the ATLAS experiment. And this is my colleague, Kiley.
Hi, my name is Kiley Kennedy and I'm a PhD student on the ATLAS experiment at Columbia University.
So we're going to be your guides today. We're going to take you on a visit. You're going to get to go not just out here at point one, the point where particles collide below our feet, but we're actually going to go down underground and see the ATLAS experiment, and that's where we collect all the data from the LHC collisions. You want to come with us? Put on your mask. You can't come down unless you got your mask on. We're going to get you a helmet when we get inside, so come along with us. All right, so everybody, we're all going to put our helmets on because we're going to go underground. We're going to be almost 100 meters underground. That's where the Large Hadron Collider collides protons together in our detector. Kiley, lead the way. Kiley's going to head on through our personal access device, or pad, and it's going to check to make sure that she is who she says she is. It's going to check her eyes here with the iris scanner. We're all going to go through. I'm going to go in through next. Okay, everybody ready? You got your helmets on? We're going to push the button and call the elevator up. It's only 2 floors down, but 2 floors down is more than 90 meters. Let me show you where we're going to go. If you take a look over here, you can see what our beautiful little detector looks like. This here, this is wrong. It's 46 meters. I know, I've seen it. It's a long distance from one end to the other. It's a very, very large detector. The whole point is that we surround the collision point. The protons come in here and they collide in the center of that detector. And we produce little people. No, we don't produce little people. These are physicists. That's the actual size of the people who are down there. And so we might see some people now. The LHC is not in operation. Don't worry about that. There are no collisions. We're all working on our detectors. This is a long shutdown. All of the different experiments are working on their detectors, and the people who give us beam, the LHC engineers and scientists, are working to give us better beam with more collisions per second in another year and a half we're going to have that. Okay, let's go down. Take us down. We're going to go all the way down to the bottom. -2. Only 2 floors, like I said, but that first step is a big one.
But if you look right here, you can see this number here shows how many meters below the surface of the ground we are. You can see how rapidly down we're moving to access the detector cavern.
We go underground basically because we couldn't afford the land above ground, right? But the whole accelerator, which is 27 kilometers around, is all buried underground. There are 4 places on the Large Hadron Collider where the protons collide. We surround them with detectors. We're at ATLAS, point 1 of the LHC. There are 3 other experiments. If we go around that way, there's the ATLAS experiment. Other direction, there's CMS, and over there's LHCb. They're all very, very important, very beautiful experiments with thousands of people working in collaborations on the experiments. We've made it. We're down at the bottom. One more time, we're going to go through. Kiley, do you want to go
Sure.
first? Okay, we're going to take you inside where you can see the detector. Now here's the thing. You're going to see an enormous device, and you're not even going to see the whole of it. You're going to see parts at a time. We have this entire huge device we're going to take you to see, and it's designed to look at the absolute smallest things that exist in our universe. In fact, can't even say large or small, can we? They're fundamental particles that we're looking at, which have no volume at all, right?
That we know of.
That we know.
That we know of.
We will always measure that.
In fact, when we refer to the size of particles, we're not actually referring to the volume that particles take up. We're actually referring to the masses of particles, which we can actually measure more precisely, because of course the volume of particles is something we really don't quite know about. And if we did know the volume of particles, it would unlock a lot of key mysteries.
Well, I think it would then mean that they're not fundamental, probably.
Yeah, it could
right?
be.
Heisenberg, I don't know, says that we're never really going to know, right? We can never tell exactly when the size is of a particle.
Yeah.
We can't tell its position exactly if we know how much it's moving, and we can't tell how much it's moving if we know its position. It's a strange world, but we're going to take you to see a little bit of that world now. We're at the far end of the experiment. These are called, this is the muon spectrometer. These are tubes filled with gas and a wire in between. When a charged particle goes through this, it leaves a trace.
It ionizes the gas.
Exactly, it ionizes the gas and sends a charge, which we read out with the electronics. We have to connect the dots to see the track of the particle that goes through. What's really cool here, what I really like, if you take a look here, that's the LHC. See the blue there? If you go underneath that, you're under the LHC.
So the actual tube that the protons go in when they're traveling through the LHC is only about this big. But if you look here, you see what Stephen is touching right now. That huge object is beam shielding that surrounds these tiny proton-proton beams, because as the protons are moving around in a circle, they're accelerating because their direction is changing, and so they emit showers of particles by this kind of circular acceleration. And close to the detectors, we don't want that stray radiation to interfere with the measurements we're trying to obtain from the proton-proton collisions. So we have this massive, massive beam shielding that you can see is probably a couple meters across.
So I mentioned how enormous this device is, and you're going to see better when we get upstairs. But I want to show you something that we do here. All these little devices here were made to line up the detector. Now you can see it's fairly precise. This gets us within, say, millimeters here. But we actually line the entire detector up within tens of microns. Tens of microns, the thickness of your hair. And that's over something which is 26 meters in diameter. That's what we have to do to get the precision measurements, to get the most out of the data that we get.
So something I just want to point out, and is something that you'll see throughout the rest of this tour, is how many cables and how many wires we have inside just this room, this cavern. In fact, if you took all of the cables that we have in this room and lined them up from end to end, it would reach to the moon and back with some to spare.
And we made it. The top of the ATLAS experiment at the LHC. I'm so glad that you could make it all the way up here with us. And now, let me answer this one question that you seem to keep asking, is like, why? Why are we doing all this? Why did we build such an enormous device? Why did thousands of people from all over the globe come together to do this? This is no easy task. Why did they all go to their funding agencies and ask for resources to do this? And why do human beings say, yes, absolutely, this is something to do? It's fundamental research. Maybe there are some questions that you could answer or maybe ask that we're trying to seek the answers to here.
Yeah, so I think the fundamental question that us as physicists are interested in is why are we here? Why is the universe the way that it is? And what are we made out of? And so these kind of questions go back all the way to the beginning of the universe, to the origin of the universe, the Big Bang. And so right after the Big Bang, all of the stars in our galaxy and all of the galaxies in the universe were compressed into a tiny volume. And everything, as you can kind of imagine, was super, super dense and super energetic. And so the types of physics interactions and processes were very different back then than they are today. And so we need a specialized system to try to study those early interactions of that very hot and dense universe. And so the way that we've approached this way to study these particles is by simulating, so kind of trying to recreate the conditions of the universe right after the Big Bang. And that's by colliding these protons at these really, really high energies to try to recreate that high energy universe. And so you can see here, if we look down into the detector, you can see kind of through all of these different highly complex layers of the detector is the actual interaction point where we see those two protons come together and collide. And we have a myriad of various layers of the detector that perform different measurements so that when we put it all together, we can identify the kinds of particles and their energies that emerge from these high energy collisions to better study what's actually happening.
Our field really started because we saw that there were these particles we couldn't understand that were kind of messengers from the Big Bang hitting us over the head. There's cosmic particles that come through us all of the time. What we found out from them is that there's a lot more out there than what we're made out of. Ourselves, I don't know about Kiley, but I'm made up of up quarks and down quarks and electrons, and I think she is too. That's what makes up pretty much all of the matter that we know, because those are stable particles. But if you add energy, you can actually create mass, right? E equals mc squared. That's what goes on down here. We take light particles, stable particles, we add a lot of energy, and then in the collisions we can produce more massive particles. The E becomes mc squared. Those particles can then transform to the lighter particles and we get E again. The mc squared goes back to E. We have to reconstruct all that, and we learn about these particles that existed in early time and which can be produced by interactions out in space as well. This tells us about the basic fundamental building blocks of our universe. That's what we care about. Fundamental particles, particles that aren't made up of other particles. We think we have a pretty good model now. We're pretty happy with it. We can put it all on a coffee cup even. We have the particles, and we have on the other side of the coffee cup an equation that explains how they interact. We're kind of happy, except that's about, what, 5% of the universe that we understand. There's a lot of other stuff out there that we're missing. What are we missing? We're missing stuff, right?
So I think we can do a lot of things very well, and I just want to point that out. What we call the standard model of particle physics, which was developed in the 1970s, and which, since its development, piece by piece, particle by particle, we've discovered every single particle predicted by this physics model in the 70s. It's one of the most precise, if not the most precise, model in science that has ever been created by humanity, or that we know of. However, as Steve just pointed out, it only describes 5% of our physical universe. And so we know there is so much more out there that we need to study to really understand the fundamental nature and the fundamental building blocks of our universe. And that's something we're trying to do here. So physicists are looking to study extensions of the standard model. So the standard model, we know it can't be the only be-all and end-all physics model. So people are looking to add particles to the standard model to explain various kind of questionable phenomena that we have observed so far. One of those being dark matter. So dark matter is about 20 to 25% of our universe, and astronomers and astrophysicists have measured this, except we don't yet know what particle or set of particles is responsible for our observations of dark matter, and we have good reason to think it is indeed a physical form of matter. And so that's one of many things that we are trying to create here at the LHC in conjunction with thousands of other scientists and other collaborations and theorists and phenomenologists who also are interested in studying dark matter. And that's just one topic of many.
Then the other dark thing that we're missing, it's great because our great-grandchildren are going to laugh at the fact that we call these things dark just because we didn't know what they are. But that's why science is so fascinating. We're looking for stuff we don't understand yet. The other thing that's dark, we call dark energy, and that's most of the universe, right? That's whatever energy is out there that's making us expand faster and faster. The universe itself is growing and going at a faster and faster rate We don't get that, and a lot of people don't get that. It's not clear particle physics will answer that. Could take other forms of physics, could be astronomy will give us some answers, astrophysics, we don't know. But we have a lot of big questions, and we're going to try to answer them. And that's why we're continuing. We're upgrading this. We're upgrading the LHC. We're going to do that again later on. It's all planned. And then we're going to look to do something even higher energy, because that's what we have to do. We're human beings. We're curious. We got to find the answers. Maybe now we should go back down halfway and take a look where you can get a little better view of the detector itself. You guys ready for that? You're not too winded, are you? Come on, let's go on down. Now you have a view you might be able to comprehend a little better here. So what do you think of that, huh? So let me explain a little bit here. What you can see from here on is what we call the barrel part of our detector. So that's the central part. The beam comes in all the way through and collides in the center of the barrel there. That's one of our enormous magnets. We have a couple magnet systems at the ends of the detector. So we surround our detectors with these very powerful magnets. These big tubes here are magnets as well, and that curves the particles. So when a particle is curved by the magnetic field, we can then look at how much it gets curved and figure out what its energy is, or what its momentum is what the term that we use. And you know that because the more it turns, the lower its momentum was.
There are a variety of different layers of the detector that do different measurements. And so when you have the two proton-proton beams coming and colliding, the first layer of the detector is what we call the inner tracker. And we have a specialized system which tracks the paths of charged particles that, as Stephen said, are in the presence of a magnetic field. And so we can track the bend of these charged particles very precisely. And then after we have this tracker, we have our calorimeter system. And so our calorimeters measure the energies of the particles produced in the detector, and they do that by stopping the particles and forcing the particles to deposit all of their energy into the calorimeter so that we can measure it. And that's part of the reason, another reason why we need such a big detector is because these particles produced in the collisions are so energetic that we need a thick material and a dense material to actually be able to stop particles that energetic. And so we have a couple different types of calorimeters that measure the energies of different kinds of particles. And then on the outside, we have our muon spectrometer and our magnet system, which Stephen has pointed out to you already. And the muon system is specially designed to measure these kind of funny particles called muons, which are considered the heavier cousin of the electron. They have almost the exact same properties as electrons. So as you know, typical electrons just orbiting your standard atoms that we see in day-to-day life, except the muons are heavier. And so because muons are heavier, they kind of fly through the inner part of the detector, and we can't capture them in our calorimeters. And so we have this specially designed muon spectrometer to actually be able to measure these muons, which are really important to our understanding of new physics.
These little targets here, we have targets on the detector because we actually take images with cameras to see how far the detectors move. They move over time because they're so large. And so you got to keep track of that in order to line everything up with the software down to the tens of microns of precision that we need.
See all in here, all of the rich
I've been
detail.
down there. I've been down there.
I know, all the cables.
One of the really cool things we get to do is when the shutdown is over and we're getting ready to come back on, then all of the collaboration comes, well, not all the collaboration, but whoever's around comes here, gets down on our hands and knees, we put on gloves, and we pick up anything and everything. Because when you have a strong magnetic field, if there's a little screw that's on the ground that we forgot, it can shoot out like a bullet. So we have to clean everything up. Your head out over there. And take a look, and you're going to see part of our detector. That's the small wheel that's sitting out in the middle there. We're working day and night to be able to replace that with, okay, catch this name, the new small wheel. We're working on those for many years now. It's a very important upgrade.
What we're doing right now is a trigger upgrade, and I'll explain what a trigger is. So in the ATLAS detector, we see 40 million proton-proton collisions per second. However, unfortunately, we can't write all of those to disk. We can't save all of those proton-proton collisions. In fact, we can only save about 1,000 per second of the 40 million. And the reason why, some people ask, why do we even have 40 million per second when we only write 1,000? And that's because not every collision is created equal. It's incredibly difficult to actually collide two objects as tiny as protons. And so sometimes we get what we call hard interactions, which is when the protons really collide head on. And then sometimes you produce glancing interactions. And so the collisions that have these hard head-on interactions, those are the ones that are likely to produce collisions that we're really interested in, that we want to keep to study. And so we have a very elaborate method of determining very, very quickly, do we keep this event or do we not keep this event? And so right now, we're improving, we're doing a number of different hardware upgrades on all of these different detecting subsystems to improve the quality of our trigger so that we're not accidentally throwing out events that we might actually be interested in. And so some of you may know the last elementary particle we discovered here at CERN and the LHC was the Higgs boson in 2012. And so now in 2020, it's been 8 years and we haven't found anything else. And so some people are wondering, maybe we're accidentally throwing those events away, and so without even knowing it. And so this trigger upgrade is really important because it might help us keep the events that have this new physics that might help us discover a new particle or new interaction or new physical phenomena.
Yeah, that's a really good point. Now, just to be clear, we haven't found any other fundamental particles.
Yes, elementary, yeah.
Exactly.
Elementary.
But we have, there's been a lot of amazing things going on. Not just at ATLAS. ATLAS, we've seen some really cool things you would never believe, like light scattering off of light. Okay? It's a really, really rare phenomenon, but it can happen. It's predicted, and we see that. We can produce things, even not just light scattering, but light hitting each other and producing matter. And that's really an incredible thing to see.
So if you look up, you can maybe you can see the surface. So we have this tunnel, this opening, and that's where we raise and lower equipment to build this detector. And so, our detector is much bigger than the opening above, and so it was kind of built like a ship in a bottle, bringing small pieces down and constructing them down below the surface in this cavern. Right now we're entering the service cavern next to the detector. And so we're not actually in the detector cavern right now. We're in a cavern slightly adjacent to it. The detector is actually kind of through that wall down there. And part of the reason why we have this cavern here is because this is accessible to people while we're taking data, while we have proton-proton beams in the next room in the detector. Because normally when we're taking data, no one can go into the detector when we have these proton-proton collisions because of the extremely high radiation levels. They're not safe for humans. And so we put a lot of machinery that we need to collect data from our detector in this room so that in case something breaks or in case we need to modify something, people can come down here. We're a little less than 100 meters underground. People can come down here and work with the machinery. So I just want to give you a little sense of the extent of all of the computational resources we're working with. It might be a little loud in there, but I'll just give you a bit of a walk around. we have all of these racks of computers, and these are responsible for everything from high voltage control to triggering to actual data taking, and the computers we use to control the detector, to monitor the detector to make sure that it's responsive and it's doing what we want to do. And again, you can see here we have all of these cables. A lot of these cables actually end up in the detector itself. And so I just want to show you all of these thick black cables here and then all the way down here. This is our current, this is the system that's currently responsible for our trigger. And so all of this is analog. And so all of these wires are coming out of the detector and are the first system to read any information from the proton-proton collisions. And so because all of this is analog, this is part of the system that we're currently upgrading to create a digital trigger that it will do a better job of discriminating between the collisions that we want to keep and the collisions that we might want to throw away. I just want to give you a sense of kind of the vastness of all of these signals that are coming out of the detector that you can actually see in virtually at least. And so even though we're doing an upgrade and the detector is constantly being modified with new hardware, that doesn't mean the detector is off. And so things are constantly running. People are making sure that as we add things, the detector is continually working. It's not like we turn it off and 2 years later we cross our fingers and hope it works. And so this level and the level below all contains these systems, these computers that help us do what we need to do. And then of course we have many more computers upstairs, and then a number of mass computing resources provided by CERN that we can't even see, don't even have time to see today.